Galileo was the experimentalist. Johannes Kepler was the theoretician. Kepler lived at the same time as Galileo, and we know they knew of each other, but they worked in different countries and Kepler did not use a telescope. Despite his personality conflicts with Tycho Brahe and their very different views on the structure of the universe, Tycho believed the Earth was at the center and Kepler believed the Sun was at the center. Despite those conflicts, Kepler worked with Tycho because Tycho had the best observational data available. Tycho was an excellent observer of the sky. Even if Tycho didn't use a telescope, his techniques were exquisite. Kepler felt that even the most elegant, mathematically harmonious theories must match reality. Kepler was motivated by his faith in God to try to discover God's plan in the universe, to, quote, read the mind of God, end quote. Kepler shared the Greek view that mathematics was the language of God. He knew that all previous models were inaccurate, so he believed that other scientists had not yet read the mind of God. Kepler tried unsuccessfully to get Copernicus's heliocentric model to fit Tycho's exquisite data. After years of failure, he was finally convinced, with great reluctance, of a revolutionary idea. God uses a different mathematical shape than the circle. This idea went against the 2,000-year-old Pythagorean paradigm of the perfect shape being a circle. Kepler's three laws of planetary motion are a radical replacement of the Pythagorean paradigm. We now know that these laws work for anything going around anything else, whether it's satellites going around asteroids, moons around planets, planets around stars, or galaxies around other galaxies. These are three laws of orbital motion. The Pythagorean paradigm is the part that is crossed out. What Kepler found follows the strikeout. Law number 1. Planets move in elliptical orbits with the Sun at one focus. An ellipse is a squashed circle that can be drawn by punching two thumbtacks into some paper, looping a string around the tacks, stretching the string with a pencil, and moving the pencil around the tacks while keeping the string taut. The figure traced out is an ellipse, and the thumbtacks are at the two focus positions of the ellipse. An oval shape, like an egg, is not an ellipse. An oval tapers at only one end, but an ellipse is tapered at both ends. Kepler had tried oval shapes, but he found they did not work. As the foci are moved farther apart from each other, the ellipse becomes more eccentric, skinnier. A circle is a special form of ellipse that has the two foci at the same point, the center of the ellipse. Law number 2. Planets move with variable speed. They speed up when getting closer to the Sun in this particular way. A line between the planet and the Sun sweeps out equal areas in equal times. The speed is fast when close to the Sun, and the speed is slow when far from the Sun. This is shown in the elliptical orbit animation. Each position tick mark along the planet's, asteroids, comets' orbit is 5 years apart from the next tick mark. When the two gray areas appear, they are equal in area. The long skinny part has the same area as the short fat part. Equal areas in equal time intervals. Objects in our solar system orbit the Sun, but the Sun is at one of the focus positions, not at the exact center of the orbit. Law number 3 tells us precisely how much longer a larger orbit will take to execute than a smaller orbit. So it refines Copernicus's earlier discovery that bigger orbits take more time. Kepler found that if you compare the orbits to the Earth's orbit, then a planet's orbital period in years squared equals the semi-major axis of the orbit in AU cubed. Time squared equals distance cubed is a shorthand way to remember it. Remember that the AU is the astronomical unit, which is the average distance of the Earth to the Sun. The elliptical orbit animation gives you one example of Kepler's third law. The semi-major axis is 25 AU. 25 cubed equals 125 squared, so this orbit takes 125 years to execute. The green orbits picture gives you 3 more examples. An orbit with semi-major axis equal to 2 AU takes 2.83 years to execute because 2 cubed equals 2.83 squared. Yes, you do need to keep straight which one has the years and which one has the AU. Years are for the time, and AU is for the distance. An orbit with semi-major axis that is twice as big, or 4 AU, takes more than twice as long to execute. 4 cubed equals 8 squared. So the orbit takes 8 years, not 2 times 2.83 years. An orbit with semi-major axis that is 3 times as big, or 6 AU, takes more than 3 times as long to execute. 6 cubed equals 14.7 squared. So the orbit takes 14.7 years, not 3 times 2.83 years. Notice that the period p, or time numbers, gets bigger faster than the corresponding distance numbers. Time is squared, but distance is cubed, so the corresponding time has to be a bigger number in order to equal the cube of the distance. On the next page of the student guide are a couple of graphs. The top graph is Kepler's third law for anything going around the sun, whether it is a planet or asteroid or comet or spacecraft or a pebble, with all the planets known to Kepler, Mercury to Saturn. The bottom graph is Kepler's third law with all of the known planets plus 3 of the dwarf planets plotted. Notice that the curve increases upward as the distance gets bigger. Also notice that it is a curve and not a straight line. That's because time squared equals distance cubed. On the back side of the plots page is a table with 401 more examples of Kepler's third law. This is a long table of 2 columns split up to fit on the page. The left column of a set is labeled A for the semi-major axis in AU, and the right column of a set is labeled P for the orbital period in years. An orbit that has a semi-major axis of 8 AU takes 22.6274 years to execute. The A column value is 8, and the P value to the right of it is 22.6274. If you are given the time, or p-value, you can find the size of orbit semi-major axis in the A column to the left of it. If you are given a value that is in between the table values, then you need to interpolate between the table values. For example, how big is an orbit that takes exactly 16.0000 years to execute? You are given a time number, so you go down the p column to the values that straddle each side of 16.0000. There is an orbit with p-value equals 15.8129 and corresponding semi-major axis A value equals 6.3 AU, and an orbit with p-value equals 16.1909 and a corresponding semi-major axis A value equaled 6.4 AU. Therefore, the orbit that has a p-value of exactly 16.0000 years will have a semi-major axis A value between 6.3 and 6.4 AU. You can do a little algebra to calculate the actual semi-major axis is 6.3496 AU. Note that the Kepler third law graphs and table work for anything going around the sun, regardless of the mass or size of the object or the eccentricity of its orbit. Speaking of eccentricity, the eccentricity measures how far from a circular shape is the ellipse. It's a number that varies between 0 for a perfect circle to 1 for an extremely skinny ellipse that is actually a line. The eccentricity animation shows you that as the eccentricity gets closer to 1.0, the ellipse gets skinnier and the focus position where the sun is moves farther from the center and closer to one side. Note that each ellipse in the drawing has the same major axis, so they have the same semi-major axis. That means each orbit would take the same amount of time to execute. The skinny orbit would have speeds that change a lot, from very fast to very slow, while the more circular orbit would have moderate speeds throughout. All of the planets have orbits with eccentricities less than 0.3, which is why it was so hard to distinguish their orbits from true circles. Most comets have orbits with eccentricities greater than 0.9. I end this slide with 2 questions we'll answer in the gravity chapter. Why do planets move the way they do? What causes them to move in these elliptical orbits?